So I want you to imagine this time that we have a container, much like before. There's some gaseous particles in here, they're these down here in yellow, and that we've got a plunger in that container. And for the sake of this conversation, we want to imagine that that plunger just is able to slide up and down completely frictionless. That plunger moves very freely based on the pressure in the container. So it's important to remember this plunger will move up and down. We're not going to force it to stay at a given point in this experiment. But otherwise, this is going to sound somewhat similar to the Boyle's Law conversation that you saw in the last video. So on the left-hand side here, we're going to first consider this situation. We're going to call this scenario 1. And in scenario 1, we have gaseous particles. They're trapped in a fixed container. And we know that the ideal gas law applies. So much like I did in the Boyle's Law video with you, I'm going to say P1 V1 equals N1 R1 T1. And we can manipulate that, as we've seen before, to give us P1 V1 over N1 T1 equals R1. Remember, R is a constant. In scenario 2, what we've done is we have warmed the temperature of the gas. So the key variable that we're changing here is the temperature. We're applying heat, and we're applying it through this Bunsen burner down at the bottom. As the gas warms up, not too surprising, it's going to start to expand, and we're going to get another situation. You can see the volume here is changing a little bit. Important thing to realize here is that the gas law, the ideal gas law, still applies. So P2 this time, V2 this time, equals N2 RT2. And we can do very much the same thing. We know that P2 V2 over N2 T2 equals R2. And again, I'm just using these subscripts to remind you what scenario we were originally talking about. We're going to see in a second here some of these variables are the same. R1 and R2 are the exact same number. It's a constant. What I want to do is set these two equal to each other, much like I did in the Boyle's Law video. And I know that this expression here is true because whatever written on the left equals R, whatever written on the right equals R, so I'm just setting them equal to each other. Right? We know R is a constant. So just based on the ideal gas law, we know that as we go from situation 1 to situation 2, this relationship should hold. The first thing I want to do is get rid of the N term. So we know that N1 equals N2. There's really only one N here. It's the same number of moles on the left as it is on the right. So N1 equals N2. Sorry, I made all kinds of mistakes over here on my subscripts. That should be N1. And that should be T1. So back to my original point, the n's are equal, so we can multiply by n on both sides, and we can get to P1 V1 over T1 equals P2 V2 over T2, and we're assuming no change to n, no change to the number of particles. We're also going to make an assumption, this is where the plunger really matters, we're going to make an assumption that the volume can expand and that the pressure will therefore stay equal. If this plunger is truly free moving, then the pressure of the gas in the chamber is always going to be equal to the pressure in the environment around the container, because the pressure pushing the plunger down and the pressure pushing the plunger up will have to be equal. So we're going to be holding pressure constant essentially, which is what would happen if that plunger can move freely on its own. But notice that it's right on the diagram here. The pressure is 1 atmosphere in scenario 1. The pressure is still 1 atmosphere in scenario 2. So we are dealing with a situation where we're also assuming that pressure is constant. So if pressure is constant, then we are left with this relationship of V1 over T1 equals V2 over T2. We're just deriving this from the ideal gas law. So if, for example, the original volume in container 1, maybe the volume over here was originally, let's say, 1.0 liters, and maybe the temperature in this scenario was originally, let's say it was 300 Kelvin. And now in our new scenario, let's say that we've heated this all the way up to 350 Kelvin. We should be able to calculate the new volume that is going to take up. We should be able to calculate V2. So manipulating our equation down here, we know V2 would be equal to V1 times T2 divided by T1. Just doing a little algebra to get the V2 alone. So if we plug in those numbers, if we take the 1 liter and multiply by 350, 1 liter, that's V1, 350, that's T2, divided by T1, which is 300 Kelvin. I should get the new volume of that second scenario 2 cylinder. I'm getting that on my calculator out to 1.17 liters. So by raising the temperature from 300 Kelvin up to 350 Kelvin, we've increased the volume from 1 liter up to 1.17 liters. Comes from the ideal gas law, but this is a nice relationship to understand. It's a nice simplified way to explain why, for example, a tire loses pressure as air pressure in the cold weather. We refer to this as Charles' law. And much like Boyle's law, this actually predates the ideal gas law. We figured this out, and then it was one of the clues that led us to the ideal gas law later on down the line. So what I want you to do now is take Charles' law and try a few practice problems.